Hi, so today I'd like to talk about the quantum harmonic oscillator, but before I do that, maybe I should start with Hooke's law, a little review of the classical simple harmonic oscillator. So remember, Hooke's law states that the force that a spring exerts on a mass is equal to minus kx, where k is a spring constant, which is sort of a judge of how stiff the spring is, and x is the displacement of that spring from equilibrium. Now, the minus sign comes from the fact that it's a restoring force, so it's always trying to pull that mass back to the unstretched or compressed position of the spring, the equilibrium position. Now, to solve for what the motion of the mass on a spring is like, you set the Hooke's law force, minus kx, equal to Newton's second law, ma. And then when you solve for the acceleration, you get minus k over m times x. Now remember, the acceleration is the second derivative of the position with respect to time. And so this gives you a little differential equation where you take two derivatives of x and get back some negative constants times x. Now oftentimes we call omega squared equal to k over m. And omega would be the angular frequency of oscillation for this mass on a spring. Now when you solve that simple little differential equation, what you get back are either sine or cosine functions. Those are the only functions, other than exponentials with an I in the exponent, that you take derivatives of and you get back negative constants times the function again. Now here, x of t, it's a function of time, is a times cosine of omega t plus phi, where a is the amplitude of oscillation, omega is that angular frequency, and phi is a phase constant, so that you don't have to start your clock right when the cosine function is at 1 at time t is equal to 0. The frequency of oscillation is equal to omega over 2 pi. And of course the frequency of oscillation is 1 over the period, and the period t here is the time that it takes for one full oscillation to occur. Now the SI unit of frequency is the hertz, which is 1 cycle per second. That's the SI unit. Solving for the energy of the simple harmonic oscillator, if you assume that the spring is not damped, in other words you're dealing with no friction here, then the total energy is constant. The total mechanical energy would be the sum of the kinetic plus the potential energy. The potential energy of a simple harmonic oscillator is 1/2 kx squared. So if you sum up 1/2 mv squared, the kinetic energy, plus the potential energy, 1/2 kx squared, then you end up with a total of 1/2 ka squared, where a is the amplitude of oscillation. If you plug in for your velocity here, your velocity would be the first order derivative of the position. And if you have a cosine function, that first order derivative would give you a sine function. And then of course 1/2 kx squared here is your cosine function, and then you would square that. And of course when you sum a sine squared plus a cosine squared, that goes to 1, which leaves you with 1/2 m omega squared a squared, or 1/2 ka squared. So that proves to you that although the kinetic energy is not constant in time, and the potential energy is not constant in time, the total energy, or the sum of the kinetic plus the potential energy, is constant in time. So it's just exchanged back and forth. And of course the spring system is moving the fastest when the mass passes through that equilibrium position, and the potential energy is largest at the extrema at maximum displacement. Now the simple harmonic oscillator isn't necessarily an interesting system in and of itself, but the simple harmonic oscillator is a model system for a lot of other systems. In particular, in quantum mechanics, it can often be used as a model system for the bonds in between neighboring atoms and solids. Okay? So if you look at what the potential energy function really is for two atoms next to each other in a solid, then you get something more like the orange curve here. If you plot the potential energy, it goes towards infinity as the potential goes to the displacement, or the distance between the atoms going to 0. And then it comes down, and then on the right hand side it's not symmetric. On the right hand side, as it tends to infinity, the potential tends to 0. But in the middle here, for small displacements from equilibrium, it's not bad to fit it with a parabola from the spring system. So it's a decent fit, and it makes a nice model system, and it's a relatively easy system to understand and solve in quantum mechanics. Now, we talked about this in a previous lecture when we talked about the uncertainty principle, but it's important maybe for a reminder or a refresher here. If you have a quantum system, you can't ever really say that the velocity or the momentum of that particle is really zero at any time. In other words, for quantum systems, it's really difficult to say that that particle is coming to rest and is absolutely still. If that were the case, then you'd know exactly what the momentum of that particle is, and your uncertainty of the momentum would be zero. If the momentum of the particle's if the uncertainty of the particle's momentum is zero, that delta p goes to zero, then by the Heisenberg uncertainty principle, your uncertainty in the position has to blow up or go towards infinity, and that's not very physical. So the reality is that even when a particle is in its absolute lowest energy state, it's still moving around. This is unlike Maxwell-Boltzmann classical distributions for ideal gases and such, where you think of the particles in an ideal gas as being absolutely still and all molecular motion ceasing at absolute zero. That's not really a very physical system if you think about the uncertainty principle and the restriction on quantum particles. You can use the uncertainty principle and the definition of the mechanical energy of a system to estimate what the lowest possible energy state for a quantum harmonic oscillator would be. Looking at the uncertainty principle, delta x delta p is greater than or equal to h bar over 2. And then looking at the energy is going to be a sum of the kinetic plus the potential energy. So here you would have E is delta p squared over 2m plus 1/2 k delta x squared over 2m, or delta x squared. And then k is m omega squared here, okay? Summing that up, this would give you your minimum possible energy. Now, you can find what the minimum of that is, that minimum of that function is, by taking the derivative and setting it equal to 0. Okay? So first of all, we've plugged in for what delta x is here using the uncertainty principle. So here you have delta p is greater than or equal to h bar over 2 delta x. I plugged that in for the delta p here in this expression, giving me h bar squared over 8m delta x squared plus 1/2 m omega squared delta x squared. Then I'm going to minimize that function by taking the derivative and setting it equal to 0, as I've done here. Negative h bar squared over 4m delta x cubed plus m omega squared delta x is equal to 0. Then I solve for delta x, and I get delta x is equal to the square root of h bar over 2m omega. Now if I take that value and plug it back into my expression for the energy that I had earlier, then I end up with h bar omega over 2 for the minimum possible energy of my quantum harmonic oscillator. And this turns out to be the correct answer when we solve the Schrodinger equation. Now, if we solve the Schrodinger equation for the quantum harmonic oscillator, basically what you do is you plug in the potential energy into the Schrodinger equation. We're going to use 1/2 m omega squared x squared as our potential energy and plug that in. And then in one dimension we end up with minus h bar squared over 2m times the second order derivative of my wave function plus 1/2 m omega squared x squared times my wave function is equal to the energy times the wave function again. Okay? Now yet again, we're only going to be dealing here with non-time dependent potentials, and so we can use the steady state Schrodinger equation to solve this problem. Now solving the quantum harmonic oscillator problem is a little bit too involved for this simple online lecture. But suffice it to say that what you have to do is you have to do some substitutions to get a unitless differential equation. So you solve for alpha is 2e over h bar omega, and you switch variables to y, and y is going to be the square root of m omega over h bar times x. Okay? When you do your change of variables, you get the second order derivative of your wave function with respect to y plus alpha minus y squared times your wave function again is equal to 0. Now what you get here is you have a wave function, you're taking two derivatives of that wave function, and you're getting back some polynomials times your wave function again. So that says to you that you should guess the solution of this form, where you have some polynomial f of y times e to the minus y squared over 2. Now, if you take derivatives of this e to the minus y squared over 2, what you're going to get back is some functions of y times e to the minus y squared over 2 again, okay? It can't just be a polynomial, right? If you take the derivative of just the polynomial 2 times, you're not going to get the same polynomial again. And that's what this e to the minus y squared over 2 is for, so that you can take some derivatives of it and get back a polynomial again times the same wave function. So that's the guess, right? Now, if you take that and you plug that guess into this differential equation here, what you'll end up with is this function down here. You can either take my word for it or you can do the math, okay? So you're going to end up with e to the minus y squared over 2 times the second order derivative of f minus 2y times the first order derivative of f plus alpha minus 1 times f, and that's equal to 0. Now I go through this in class, by the way, okay? So if you miss class, you can get the notes from somebody else. But this function right here, this differential equation right here with the second order derivatives of f, neglecting this e to the minus y squared over 2 out front, that's actually a very famous differential equation. And it was solved by Hermite. And the solutions to that differential equation look like this. So these are the Hermite polynomials. And you can see here they're all plotted on top of one another, and so it's kind of a mess. But the take-home message is that it kind of looks for many of these like they're oscillating, sort of like they're wave functions. Also, another take-home message is there's an infinite number of solutions to this differential equation. They go up in order of x. So the Hermite polynomials start with h0, and then it's just 1, the constant 1. And then you have your first order solution, h1, which is 2x, and so on and so forth, okay? So that tells me, hey, energy levels, right? Quantum energy levels. Great. So the Hermite polynomials, they dominate inside that potential well for small x. There's a Gaussian function on the outside, that e to the minus y squared over 2, and that multiplies the Hermite polynomials. And that helps because as your position goes infinitely far away from your equilibrium position, your probability of existing there should go to 0, right? You don't want your wave function to blow up for large values of x. And so that Gaussian function sort of damps that wave function out for large values far from the equilibrium displacements. And that helps, okay? That helps satisfy the conditions on the wave function. It forces the wave function to eventually go to 0 outside of the well, which makes sense. Now, the full solution to the Schrodinger equation for the quantum harmonic oscillator, they look like this. So in this little cartoon, the wave functions are pictured here on the left, and the probability density function, which is the square of the wave function, is pictured here on the right, okay? At the bottom is the ground state, and then going up from there, first excited state, second excited state, and so on and so forth. One thing to take home is that you've got a certain number of humps in the wave function, and that number of humps kind of gives you the answer to the energy level. So if you've got one hump here, basically a Gaussian function, then that is the ground state. 2 humps, first excited state. 3 humps, second excited state, and so on and so forth, okay? Hump, by the way, here is a very technical term. Now, if you solve for what the energy levels are for this quantum harmonic oscillator, you get evenly spaced energy levels, as shown here in this little cartoon. Zooming in and looking at the cartoon a little bit more in depth and discussing what these energy levels actually are, the equation for the energy levels is n plus 1/2 times h bar omega, or n plus 1/2 hf, which is basically the same thing, okay? Now, the energy levels are going to be spaced by h bar omega. So your ground state is 1/2 h bar omega, your first excited state is 3/2 h bar omega, and the difference in between those energy levels is h bar omega, okay? And they go up from there, 1/2, 3/2, 5/2, 7/2, so on and so forth, okay? Now, in that equation, n plus 1/2 h bar omega, n is equal to 0 for the ground state. Now, this confuses everybody the very first time they see it, because for the other quantum systems that we've solved, like the infinite square well or the hydrogen atom, n starts at 1 for the ground state. So you're just going to have to remember that the principal quantum number starts at 0 for the quantum harmonic oscillator, and it starts to 1 for many of the other systems that you're studying in this course. Sorry about that. That's just the way it is. Now, we could make this a little less confusing, I guess, by using a different variable instead of n to define that parameter. But it's kind of how it's done in a lot of textbooks, so you may as well start getting used to it now. I don't know why we didn't call it a different letter. I didn't make up the rules, okay? But the reason that it really is that it starts at n equal to 0 for the ground state, is yet again because of those Hermite polynomials, which are the solutions to our quantum harmonic oscillator problem. In other words, the n equal to 0 corresponds to the power of x that the polynomial is at that energy level. So here, n equal to 0, x to the 0, it's all constants for the first energy level. And then n equal to 1, that's where you get your harmonic polynomial being linear. N equal to 2, you've got an x squared in there, and so on and so forth. Okay, so that's why they are the way they are. Let me do a couple of example problems for you for these quantum harmonic oscillator problems. In the first one, I'm trying to highlight why classical oscillators don't look quantized. So here we go. A simple pendulum has a 100-gram mass attached to a 1-meter long string. It swings to a maximum height of 1 centimeter above the lowest point. And what would be the corresponding energy level in the quantum harmonic oscillator? So the frequency of a simple pendulum is 1 over 2 pi times the square root of g over L. You should have learned this in your introductory physics class, but if not, there's a lot of hyperphysics websites that'll help you out. Now g here is the acceleration due to gravity at sea level, which is 9.8 meters per second squared, and L is the length of the string, which is 1 meter. So if you plug this in, you get a frequency for your simple pendulum of 0.5 hertz. Now, what you do to solve for what the energy level would be is you plug in the energy that the classical system has, and then set that equal to the equation for the energy levels in a simple harmonic or in a quantum harmonic oscillator. So in other words, you have n plus 1/2 times hf, and that's going to be equal to mgh, the potential energy, the gravitational potential energy for a mass that would be, in this case, 1 centimeter above the origin. So our mass is 100 grams. Let's plug that in, 0.1 kilograms. G, yet again, is 9.8 meters per second squared, and the height is 1 centimeter, or 0.01 meters. Solving for what hf is, plugging in f is equal to 0.5 hertz, and h is equal to 6.626 times 10 to the minus 34 joules seconds, we arrive at our value of n, which is 2.97 times 10 to the 31. Now this is an enormous number. So the punchline is that in a classical oscillator, you wouldn't notice the quantum effects. And that's because the energy levels are spaced so closely together that everything appears continuous for a classical harmonic oscillator. So you don't see them. And it's only when you start scaling the system way down that you start seeing those quantum effects. Let me do another example problem for you. Here, we're dealing with a real, true quantum harmonic oscillator, and we've got an electron that's confined in a harmonic potential well, and the effective spring constant is 5 newtons per meter. So what wavelength photon would be emitted if the electron jumped from an n equal to 6 energy level to an n equal to 3 energy level? Okay? So the solution here would be to solve first for what omega is. Omega would be equal to the square root of k over m, just like in a classical oscillator. K here is 5 newtons per meter, and m would be the mass of that electron, which is 9.11 times 10 to the minus 31 kilograms. So when we solve for that, we get an angular frequency of 2.34 times 10 to the 15 radians per second. Now, the energy that the photon the energy of the photon that would be emitted is equal to the difference in the energy levels. In other words, energy is going to be conserved in this system. So any energy lost by that electron when it jumps from a higher energy state to a lower energy state is going to be emitted in the form of a photon. So our energy levels are n plus 1/2 h bar omega. Now if n is equal to 6, then n plus 1/2 is 13 halves. And if n is equal to 3, then n plus 1/2 is 7 halves. So if I subtract those two energy levels, 13 halves h bar omega minus 7 halves h bar omega, then I get 3 h bar omega, which would be the energy of my photon. Now I've already solved for omega. I just multiply that times 3 and then times h bar, which is 1.055 times 10 to the minus 34 joules seconds. When I do that, I get an energy for my photon of 2.47 times 10 to the minus 19 joules. Now that's emitted in the form of a photon, and the energy of a photon is equal to hc over lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength of the photon. Plugging in those values, I get a wavelength of 804 nanometers. So that would be the wavelength of the photon that would be emitted if it made that energy level jump. Okay, so with that, I'm going to close there. Like I said in class, I'll go over a little bit more in exactly how the solution to the quantum harmonic oscillator goes, plugging in, showing you Hermite's differential equation and all that, but it's a little involved for the online lecture. Suffice it to say, this should help get you through your homework. I hope you enjoyed it, and I'll see you in class.